So now you see this has been done. You have prepared the sample, you have done it, you have taken the pictures. Now in our lab, the microscope is a very costly microscope. We bought it several years ago for about 40,000 reals plus. It's a very costly microscope. So a computer is attached with it, and once we are happy with our image, we take an image at 100 micro magnification, we save it. We take it at 200 magnification, we save it. We take it 500 magnification, we save it. So those we do, and we do not put any USBs or anything there, because we do not want to damage the machine and its high level software, very costly software with any viruses and so on. So every time we do some work, we put a brand new CD or DVD inside, and we take the images, and then we send it to all of you. So now the grains and the grain boundaries are available. So one thing that we now want to do, quantify it, right? Find the quantity. So we know earlier we have told you that the grain size depends, right? Grain size tells you what mechanical properties will be there. When we were doing chapter 6, if you remember, we told you that if the grain size is smaller, then the strength of the material is higher. We had the Hall-Petch equation, if you remember, which related the yield strength of the material to the average grain size of the material, right? At that time, we just showed you the equation, but now you can see that after doing the microscopy, you can find the grain size, and therefore then you can, if study the mechanical properties and what are there and so forth, right? So one thing is there, that if the grains are fine, then the mechanical properties will be more uniform. If the grains are large, some are small, some are medium, and so on, so the properties are not the same everywhere. When the grains are a small size, then the grain size is roughly the same everywhere in the metal, so the mechanical properties are uniform, they are the same everywhere, which is very, very important. Otherwise, if the grains are slightly larger and the properties are not uniform, at one place the yield strength is different, at another place the yield strength is different, then we don't know what is the real yield strength of the material. So fine grain size is good in two ways now. First, fine grain size means higher strength of the material. Second, fine grain size means that the material properties are uniform. Okay, so we will study about the grain size now. Now, we have told you ASTM is the American Society of Testing and Materials. American Society of Testing and Materials. It is the largest organization in the world which publishes standards of how different experiments should be done, right? Tensile test, hardness test, compression test, torsion test, thousands and thousands of different tests. How should be they done? There is a big committee in the world, and experts are there, and they have written documents of 3, 4, 5, 6 pages, that what will be the machine used, how will the sample be there, what will be the sample geometry, exactly what will be the steps of the testing, and so on, so that anybody who does the test anywhere in the world, whether they are in the US or Europe or Asia, they do the test exactly in a similar standard manner. So ASTM is that organization. ASTM defines something called a grain size number, a small n, grain size number. It is a measure of the grain size of the material. So capital N is 2 raised to n minus 1, where capital N is the number of grains per square inch when we have done the microscopy at 100 magnification. This is standardized. Remember that we have prepared a sample and we are looking at it under a microscope, and we have set the microscope to 100 magnification. You see, in the microscope there are many lenses and so on. So when we set it at 100, one particular lens is used. When you set it at 200, another lens is used. When you set it at 500, another lens is used. So inside the microscope we set it at 100 magnification, and then in 1 square inch of our image that we see, we count the number of grains. Count the number of grains, right? We can either do it physically or some software can do it. So the number of grains in 1 square inch of the image, which is seen at 100 magnification, that is capital N. And when you put it in this equation, then you can find the small n, which will be the grain size number for this metal, right? So this is it. Now, if this small n is less than 3, then we say it is very coarse grained material. Coarse, is opposite of fine. When n is between 4 and 6, it is medium grained. When n is between 7 and 9, it is fine grained. And if n is greater than 10, then it is ultra fine grained, right? So this grain size number tells us how fine, how small the grain sizes are. And we know that if the grain size number that we find from here is ultra fine, then the grains are very, very fine. So the strength and so on will be very high and so forth, right? So this way we find the grain size number of any metal, for which we have done the grinding, polishing, everything, and we see it under the microscope at a magnification of 100. And in that image, 1 square inch of that image, we count the number of grains, which become the capital number n, and from there we find the small n, which is the ASTM grain size number. Here there is a table that grain size number 1 to 10, right? How many grains we see in 1 square millimeter and how many grains we see at a magnification of 100. You see, this is magnification of 1, normal, without any microscope. So in 1 square millimeter, how many grains do we see? But if we see it under the microscope, then this is the standard. We see at 100 magnification and we find the number of grains in 1 square inch. So n is equal to 1 means there will be 1 grain per square inch. And n is equal to 10 means that there will be 512 grains that we can count in 1 square inch of the material at 100 magnification. So this is the details. And now we find the grain size number. So now after the microscopy, we have done one quantifiable thing, right? We have done one measurement, something which is a number, which is the grain size number. Here then we are showing you just as an example that this is 1018 cold rolled steel. This is one type of steel and the grain size number is 10, right? So this is very fine. So we see very, very, very small grains. This is 1045 cold rolled steel. It is a grain size number, ASTM grain size number of 8. So the grains are fine but slightly bigger than this, right? Very fine is very small and this is slightly bigger. So this is grain size number of 8. Right. Similarly, here we are just showing you that ASTM grain size number, low carbon steel, which is the normal steel at a magnification of 100. This is grain size 7. This is grain size 8. This is grain size 9. So you see, as the grain size number increases, this is slightly larger grains, then smaller grains, then finer grains, and so forth. So of course, at our level, this is more than enough. If we actually had done the microscopy in the lab, then we will say that, please excuse me about my throat. So we will tell you that in the microscope, select 100 magnification and then take the picture and record it. And then that picture, when you print it, then take any area of 1 square inch, 1 inch by 1 inch by 1 inch by 1 inch. And in that area, count the number of grains. So that you will find the capital N, that this is the number of grains that you see in 1 square inch of the image, which is at 100 magnification. And then you will find the ASTM grain size number and so on. So at our level, this is enough. Average grain diameter. You see, I just reminded you of the Hall-Petch equation, where the yield strength was a function of the average grain diameter, right? So therefore, now if we can find this quantity, the average grain diameter, then we can go to the Hall-Petch equation and we can predict the average yield strength of the material. So this will be huge, that we have not done any tensile test. Tensile test is done at the macro level, right? But we are taking a very small piece of the material. We are taking a very small piece of the material and we are, and we are doing only microscopy in nanometers. But once we do the microscopy, then of course we see the grain structure and this and that. But from this grain structure, if we can find the average grain diameter, then we can predict that the material property called yield strength will be so much. So for that, we have one equation. This equation is there. This D is a number that we want to find out. And this D is C divided by NLM. So NL is the length of line, right? So we take the magnified image of the microstructure. We take that, okay, we will take a line of say 1 centimeter, and we will count the numbers of grains intersected, by this line, right? So NL is the length of the line, C is a constant, and for normal microstructure, C is taken to be 1.5, and M is the magnification. So if it is 100, then the magnification is 100. If it is 200, then it is 200, and so on, right? So this is an equation which we also use. We will not use this equation ourselves too much, but it is just a thing that if we want to find the average grain diameter, then this is one way of doing it. So you see here, for example, we are seeing this microstructure, right? Suppose it is at 100 magnification. We draw a line of 3 inches, and we see that we count that it is cutting 5 grains. So that is the number of grains that we are cutting it. And then we put it into our equation that the length of the line was 3 inches and the number of grains that it intersected was 5. So we put it into the equation and then we find out. Okay. So let us do an example. We usually try to do that. Let us do an example. An ASTM grain size determination is being made from a photomicrograph of a metal at a magnification of 100. So the image is already at a magnification of 100. What is the ASTM grain size number of the metal if there are 64 grains per square inch? If there are 64 grains per square inch, right? So in you have done the microscopy, the image is 100 magnification, and you have counted the number of grains. It is 64 grains in 1 square inch. So what was your equation? Capital N is equal to 2 raised to small n minus 1. So in that equation, put capital N is equal to 64 and then find it out. So this is a very simple, nothing at all. This is the equation, and capital N is 64. Right, capital N is 64 because it is the number of grains that we saw in 1 square inch at 100 magnification. So 64 is equal to 2 raised to n minus 1. Take log of both the sides. Log of 64 will be n minus 1 log of 2, right? And then solve it. You find n is equal to roughly 7. You may not find it to be exact number, right? You may not find it to be exact number. So just round it off to the closest number, and then you have the ASTM grain size number. So as soon as you have done a microscopy experiment and you take an image that you record at 100 magnification, you can print it, you can save it, and you can count the number of grains at that 100 magnification 1 square inch and put that capital N is equal to here, and you are done. Okay.